Today I'm going to talk to you about the paleoseismic history of the Thousand Lake Fault, which I'll characterize for you now as a long recurrence normal fault, which may have slowed down at the very eastern edge of the basin and range. So this image that you see there is along the Thousand Lake Fault, roughly like that. In the background, we see Boulder Mountain, which sits 11,000 feet above sea level. It's relatively flat topped kind of volcanic tableland, which has been displaced across the fault, and now the valley is about 4,000 feet lower. And then we're looking kind of near the town of Bicknell, this is all near kind of Capitol Reef National Park area. And so the rocks that are displaced in the footwall we see are Mesozoic rocks such as Carmel Formation, Navajo sandstone. And right here we see this contact between that and tertiary volcanics and then quaternary alluvial fan material on the hanging wall side of the fault. I became interested in this area because I was doing a lot of teaching of geologic field camp at Utah Valley University and noticed a lot of opportunistic opportunities basically to see some expressions of the fault zone exposed, both in the bedrock and also with some younger alluvial terraces and colluvial wedges. And so we ended up getting some money to do a paleoseismic trench in our 2018 field camp, and so I'm going to present to you those results here today. As well, there was a regional collection of LiDAR data at a 1 meter scale, which was collected in 2020, so I'll present that as well. So I'd just like to acknowledge my co-authors, including Dave Marchetti at Western Colorado University, Christopher Bailey at Williams Mary College, and then we have our Utah State University OSL collaborators, as well as students, and Robert Beek from the Utah Geological Survey. So here we are at the kind of very eastern edge of the basin and range, and that map shows the Great Basin. Technically, actually, so here's the Thousand Lake Fault. It's roughly running north-south. It's about 50 kilometers long. Of course, the fault dips to the west. It's dropped down that volcanic tableland across the fault, and on the footwall side, we see these prominent, more than 11,000 feet high Boulder Mountain and Thousand Lake Mountain. Bisecting the fault is this Fremont River, which flows out through near Capitol Reef National Park and then into the Colorado River Basin. So technically we're not in the Great Basin here, we are draining into the Colorado River Basin, but we're very much at the eastern edge of the basin range. Okay, so what was previously known about the Thousand Lake Fault? So basically Utah Quaternary Fault and Fold database says that it must have had some activity in the last 750,000 years based upon faulted river terraces that formed since the start of the mid-Quaternary. And then also my co-author, Dave Marchetti, published a paper 2007 where they had very well dated some landslide deposits using helium-3 dating on volcanic boulders on the side of Boulder Mountain through a prominent trace of the Thousand Lake Fault, which was not ruptured. And so they said that the last activity must have been before 125,000 years ago. But we'll see today that it's more recent because of rupture along a different fault trace. The slip rate is characterized as just being less than 0.2 millimeters per year. And so today we'll look at the LiDAR and the paleoseismic results, which include some OSL dates to constrain the age of earthquakes. We're going to look first at the northern section here in that box. The gray area is kind of where I've roughly looked at LiDAR, although haven't spent enough time yet to characterize everything. We'll first look at the north, we'll go to the south, and then we'll go to the center, which is where the paleoseismic results are. But before we do that, we'll just think about the long-term slip history, just in case it wasn't clear. So we're looking from across the valley on the hanging wall side of the fault to Thousand Lake Mountains. There's that flat top remnant of the kind of volcanic tablelands. Here are the correlative volcanics, which are roughly about 24 million years old, dipping into the valley, underlying the valley sediments, and the expression of the most recent activity along the fault is roughly about there in the topography today. And so it's just showing you this nice marker of displacement. So that's about 1,500 to 3,000 meters of displacement since tectonic initiation. If we presume that's 10 to 16 million years ago, kind of general basin and range initiation, that gives us a slip rate of 0.1 to 0.3 millimeters per year. I'm not sure if that's true, but that's just a rough ballpark for now, which corresponds to that idea of it being around about 0.2 millimeters per year or less, but it's less. Okay, so now we're in the north, so we're up here, and we're looking here because we're on the side of Thousand Lake Mountain, and both of these flat-top mountains, they're over 11,000 feet tall. They had mountain ice sheets in the last glacial maximum, and at this location, this is the only place along Thousand Lake Mountain where the end moraines, the ice extended down across the fault zone. So the fault zone is roughly characterized here between these two yellow arrows and these two yellow arrows. You can see kind of a topographic break here in this slope shade map. And then these are the ridges of the end moraines, which roughly correspond almost exactly where the fault goes through. You can see a topographic break across here, but given this is LiDAR data, it's not very convincing that there's any recent ruptures there. There are a few small little hints of something in the moraines, and here's a little topographic profile right here, but it's not convincing to me that that topographic break is a displacement, just could be something else going on. I haven't been there in the field. But this is in contrast with in the south. Here in the south along Boulder Mountain, the fault zone is much wider. It's over 5 kilometers wide, but we're just looking here in the middle image at where the ice sheet spilled over the prominent fault scarp at the top of the mountain. And so you can see some glacial features, glacial deposits, and some kind of periglacial features on top of that. But then I think this is a moraine feature there, and the ice spilled across here. Anyways, I'm hoping that you can draw yourself right to this very sharp lineament there, which actually steps and extends on the top of the mountain. And so that lineament looks very young, and it must be younger than the last glacial maximum, which is pretty well dated to about 21,000 years ago. And it has about 2 meters of displacement across that lineament. Those breaks extend for kind of stepping, of course, for several kilometers to the north and also more to the south. And then off to the north of Boulder Mountain, there's a lot of landsliding going on, and the glacial deposits aren't there, so I can't follow them quite to where the next location we're going to is, which is the central part of the Thousand Lake Fault. So here we are near the town of Bicknell, which is located right here. This is a recent geologic map. And I just want to draw your attention to this alluvial fan. We dug a trench at the position of the arrow in the alluvial fan. So here is just an air photo. Here's a slope shade map with contours on it. There's some lineaments across here. It's a little washed out, but hopefully you can see there's some remnant fault scarps in this alluvial fan. The alluvial fan is not actively receiving water from the higher topography here anymore. Sometime between the previous glacial period and the last glacial period, the fan was abandoned as the channel was captured and it flows out there now. Based upon helium-3 dating of boulders on the mountain by Dave Marchetti, it's probably sometime since 100,000 years ago. And that corresponds to what we'll see in the trenches, so we'll talk about that next. First, we'll think about what the LiDAR shows us about displacement across the fan surface. So this is a topographic profile running from here to here. Across the whole surface, we see on the order of 4.4 to 4.8 meters of surface displacement since fan abandonment. We only dug one trench. It was located along the most prominent part of the fault scarp, the farther western portion, but not across that entire topographic relief, just kind of part of it. So it doesn't have every piece of information. So here's a trench looking to the south. In the trench, of course, we see alluvial fan stratigraphy, including fluvial deposits and debris flow deposits. Fluvial is shown in blue. Orange is representing debris flow, matrix-supported deposits. On top of that, we see overprinted a very prominent BK3 soil horizon. Across the center of the trench, we see that BK3 soil thickens. And that is across the fault zone that the thickening occurs. And you can see the base of it is lower down as well as thickened. It's about 2 meters, the base is about 2 meters displaced across the fault. Overlying that is a younger colluvial wedge, which grades into a BK1 to BK2 stage soil horizon. So we infer that there's 2 earthquakes here. We have 4 OSL dates. One was collected just below the MRE, most recent event, colluvial wedge, and that constrains earliest that earthquake could have been, which would be younger than 15 to 25,000 years ago, which corresponds to what we see with the glacial deposits being ruptured to the south and Boulder Mountain. The older event, which must have happened while the soil was developing, we can constrain to be sometime between that age of that youngest OSL age to about 60,000 years before present, the youngest OSL age within the fluvial deposits below the BK3 soil horizon. To save time, we'll skip over the North Trench and go to the results. So we see 2 events in 60,000 years in the trench, so it's pretty slow. Recurrence about 30,000 years per event. If we presume that, since we didn't see all of the displacement in that fan, but we saw about a meter of displacement per earthquake, and there's almost on the order of 5 meters of displacement in the fan, we could think that the recurrence rate could actually be anywhere in this range of about 15 to 30,000 years per event. I'll just skip down here to the bottom. The late Pleistocene slip rate based upon the displacement of the fan and the estimated age of its abandonment, which would be somewhere between 60 and 120,000 years, is less than 0.1 millimeter per year, so quite slow. So yeah, in summary, it's been active since last glacial period. We have a recurrence rate, the preferred rate is probably in the order of 20 to 25,000 years per event. It seems that it probably didn't rupture the entire fault previously, so magnitudes could range anywhere from, if it's half of a fault rupture, to about of magnitude 6.8 to 7.2 in full fault rupture. Okay, thank you.